The loop invariant will be that we have a current flow, and we build an augmentation graph which says how much more flow you can put through each edge, and you find a path through that augmentation graph. Well, we're gonna do it a lot more, but right now it's here. We got a current flow of 1, and you're allowed a flow of 2. So that's saying you can push one more through, right? And so then the question is, this is hill climbing. We keep getting a better and better flow, and the question is, do we get stuck in a local maximum, or do we find a global maximum, right? And here we're going to give you an example to show how we can get stuck in a local maximum. So we did this example before, and we came up with the optimal. And here we're going to start with, if you note, it's the exact same graph. I just moved the nodes around in order to emphasize why we're putting flow through this first edge first. And so in this, what we're going to do is we're going to run the algorithm here, and we're going to get to a flow, and we're going to be stuck, and it's not as good of a flow, right? So here, basically, we first push flow 2 through here, and then we push flow up along there, and then we push flow down along there, and we get to this spot. And now, if you take the augmentation graph, it shows you where you're allowed to push more flow, and you can see there's no path. Everybody kind of buy the concept? One yes. Excellent. Everybody remember what network flows is? Everybody got the basic algorithm here? Is we have a current flow, and the augmentation graph tells you how much you can change the flow in each edge. And so what we look for is a path through that augmentation graph. Here's a path here. It means you can change the flow along this edge and this edge and this edge. So that means we can get another drop of water through, right? And so we take this path here and see how much we can. Right here you can push another 20. Here you can push 19. Here you can push lots. So the bottleneck is 19, and we push 19 through. You following that? Right? And then here's just this graph. Right? We can get one more there and one more there and some more there, but we can't get any more through. And the problem is the total flow is 50, where what we did before was 51. Right? And so here we went one direction, and we got 51. Here we went another direction, and we got 50. And anybody see what we did wrong in this graph when we did it here? We kind of went through this example maybe too fast, so maybe you didn't see what's wrong. But here the key difference is we only have one flow through here, right? While here we started pushing flow through here, so we pushed 2 flow through here, right? And that's kind of where our mistake was. We put too much flow through that one edge, right? There's 31 plus 19 gives you a total of 50. While here we got 20 plus 31 gives you a total of 51.
So how do you determine the max flow for a network?
What is the maximum flow? Well, this flow is better than this flow, and they're both stuck. I definitely would say that you can't do better than this, because this is at capacity and this is at capacity, right? So you're not going to get any more than that, right? But here, right, here we could get more through here, right? So we can think about what went wrong is we were doing our progression, and at some point we made it a choice that took us up into this local maximum as opposed to this global maximum. Everybody get that idea? Right? And so what can we do differently? We have to fix this algorithm. Dijkstra's is going to find shortest paths. Right, so maybe Dijkstra's algorithm could help us choose which path. We're chasing different paths, and actually it's funny, were you talking about to choose which path to push through? Yeah. Actually, my father's algorithm chooses the path that has the smallest number of edges. So there, you could somehow make a choice of, oh, I could push flow through this path or this path, and you could somehow choose and make a better choice. But as it turns out, we don't know how to make a better choice. All right? The other option is when you get stuck up here, you could backtrack and try something else. And we're going to be talking about recursive backtracking, where you try different things. Anybody know what the problem with those algorithms is? Yeah, they tend to be exponential time. The other option, what we're going to try, is to define a bigger step. What does it mean to get stuck here? Is I'm only allowed small changes in my current solution. And being stuck means that if I just look at the small changes, then they're all going down. If I could make a bigger change, then maybe I would go up. So suppose we're looking down now on the same hill, and these are all the various solutions, and I'm currently at this solution, and by a small step, I mean that I can move to one of those in one step. And right now they're all going, all of these, this is the best solution of that set, right? So I'm sort of stuck there, right? And given that definition of step, we have a certain topology, right? Here I'm located here, that if I make a small change, then it's going to get worse, right? But if somehow we can make our definition of a step just a little bit bigger, then maybe that'll change the topology enough to get rid of that little valley. Does that make sense? So that's what we're going to do now, is we're going to redefine our algorithm so that it takes a bigger step. And here, as we said, the bug was that we put too much flow through this, right? So if this is actually the optimal solution, not only is it optimal, but it's the unique optimal, right? It's not always the case that the optimal is unique, but in this case it's unique. So in order to take a step and make something better, we really have to go over here, right? Somehow we have to step from here to here. Now the problem with that is we have to decrease the flow along this edge while somehow we're increasing the total flow, right? Because remember, every step we want to be making progress, so we can't decrease the total flow. So somehow we have to decrease the flow at an edge while increasing the overall flow, right? Does that make sense? Just checking. All right, so right, that's kind of what I've said already, right? So let's go back in and think about the definition of an augmentation graph. You were talking about, being clear about it, and this little bit here, a couple of times people have struggled with it, but it's pretty straightforward. It's we're not going to think right now about how much flow can go through an edge. We're going to think more about the calculus idea of how much can the flow change, right? It's the difference between what where are we currently versus how far can we move, right? So currently, we have a flow going this way of 15, and we're allowed a flow of 75, right? So if we want to think how much more can flow this way, well, everybody can see how much more can we push this way?
60.
Exactly, 75 minus the 15, right? But now let's think about how much we can change the flow this way. Well, that's the amount we can have this way is 10, right? We can have 10 this way. But we already have 15 this way. So how much can I change it in this direction? 25. So everybody see what we're doing is we're changing it this direction we're undoing this flow of 15. Right? By changing it in this direction, we're decreasing this flow to 0. And then we increase it by another 10 in the other direction, which is a total of 25. And I have a bunch of slides on that, but it's just here. Suppose the total you can go this way is 75, and the total you can go this way is 10. If I'm currently at 15, then the amount you can travel this direction, the change in this direction, is the 75 minus the 15, right? But the amount you can change in this direction is you can first undo the 15 and then do another 10. Are people kind of getting that? You can't, we don't want two flows in the same direction. I mean, in opposite direction. But you can imagine, walking this direction positively is kind of like walking in this direction negatively, right? So if I increase the flow in this direction by a negative amount, right, then it decreases this number. If I increase it in this direction, then I'm decreasing this number. Yeah?
I get that, 10 plus 15 is 25, but I don't, you're pulling it back from making negative 15 from third right away.
Yeah. All right, so here, where do we got our slides?
That one's fine. It says it's
Right, so I mean, this is kind of saying, right, if we add 5 in this direction, then it's kind of like moving over 5. And so I keep getting way too many slides here to try to explain this concept. Where did we go here? I got way too many in this topic. Oh, we're in the end. That's why. See, not only do we have so many, but these are all ones that I deleted because people got too scared with it. All right, so let's go back to right, so anyway, the point here is, you can imagine adding, if you add 5 in this direction, then the flow goes up 15. If I add negative flow in this direction, it goes down by 5, right? And so that's kind of the same as adding flow of 5 in this direction. Are you more or less getting it?
I think what I was confused about was why does it stay? Why is it 25 and not 15? Right? But then I think it's like a solid. You can't change the number.
Yeah.
So
Anyway, we're so behind that my recommendation is you go through these slides yourself, and if you're confused by it, but it's pretty straightforward. All right, so now this is where we got stuck before. All right, and we're going to build a new augmentation graph. And so, that's our old augmentation graph. We need a new one. So in the new one, how much more can we push this way? Well, we're at 19, we can push one more forward, right? So we have a directed edge going forward of 1. But I actually added a directed edge coming back of 19 because we could also undo this 19 if we wanted, right? And this edge here is an interesting, this one here is we have a flow 2 going forward. Well, we can't push any more forward, but we can undo this 2 if we want. So that's a new edge we're having come back, which says we can undo this 2. Right? And then here we can push 20 more. We have 75 minus 50. We could push 25 more, right? Or we could undo the 50 and do an extra 10, right? So this is 60, which is undoing the 50 and an extra 10. People kind of follow that? And so really the key edge that matters to us is that we didn't have an edge here before. But now we can see we can undo that 2, and it gives us more changes. So now in this graph, we look for a path, and you can see there is a path, right? And we can say, well, what's the bottleneck of that path? Well, I can push 1 more here. Here I can push 2. Here I can push 1. So the bottleneck is 1, right? So I'm going to push 1 along there, right? And now when I do that pushing, what happens is, well, when I go 1 along here, I'm adding that flow, so it goes from 19 to 20, right? But here, I'm pushing this direction 1. So how does it change? It changes by 1 down, right? We subtract off that 1, and you get the new flow, right? Everybody kind of buy that? And that's the flow that we had before, which we said was optimal. All right, so then we do it again. We have our new graph. We construct the augmentation graph. You might notice in this edge here, how can we change it? Well, we could push 1 more forward, right, to go from 1 up to 2, or we could push 1 back to go from the 1 down to 0, right? But in this graph, there's nowhere to go, right? In fact, you can't get out of S. Now, so you find a path, there's no path, so you stop. All right? So this is kind of how it came out better. So here's the code, right? We're given a graph with directed edges and capacities on the edges, and a node S and a node T, and your goal is to find the max flow. We're actually also going to find the min cut, but we haven't really talked that much about that yet. We start with the 0 flow, and our loop invariant is that we always have a legal flow. What's a legal flow? Is every flow is less than the capacity of the edge, for each edge, the flow, and for each node, the flow in, total flow in equals the total flow out, right? And then what do? We build our augmentation graph, given our current flow. And how does the augmentation graph change? Well, the amount you can flow from U to V is the capacity from U to V minus the current flow, right? And then the augmentation from V back to U, right, is you can undo the current flow from U to V and then the capacity in the other direction. All right. Oh, so then you have the augmentation graph, and then you find a path from S to T, and if there's a path, then you find the minimum capacity along that path, and you add that amount along the path, and if it's in the reverse direction, you subtract it. Are people kind of following this? And then if there's not a path, then we're going to talk about how to form a cut and what that means. All right, so here's an example. I think we talked about all the divorces that are going to happen. Remember, here was a path. Here, three people are getting married. And if you look at the augmentation graph, in fact, I think I bring the augmentation graph up here. Right, so there's 4 solutions. So if we currently have 3 matches and we form the augmentation graph, it's the blue is we have, I guess the red is where we've matched. Right, so here we put flow there, we put flow there, we put flow there. We've matched those people, right? And the blue is where we don't have matches. So what's our augmentation graph is where there's blue, we can push more flow, right? And when we have flow already, we can undo that flow, right? So if we look for a path in this graph from S to T, well, there's only one path, right? It goes, well, there's no path. Oh, no, here. You come down here, right? You flow down here, and then you're coming up here. And as you come up here, this person is marrying that person. And then you come down here, this person's divorcing, and this person's marrying, and this person's divorcing, and then marrying and divorcing and marrying. Right? Find that path, and there's your augmentation path. And the joy about it is when you're going this way, you're adding an edge, and when you're going this way, you're removing an edge. But we start going this way, so we start by adding an edge, and we end by adding an edge. So in the end, one more edge gets put in, right? Right. So when we go this way, we add an edge, right? Because we're adding flow along here. When we come back, we remove an edge. So it's this alternating between adding and removing. But we start by adding, and we end by adding, so there's one more adding than removing, right? And so we have an increase in flow of 1. Everybody see this example? And so you get a new flow, you get more people married,